months ago, 10 months ago, I got so frustrated with trying to do imaging and take pictures and set up telescopes, I shut the whole thing. Had I been in a worse mood, I probably would have taken a baseball bat to the whole setup. I was just fed up with it. Well, then I ran across the guy that you heard talk last month, Professor Paris. Hopefully many of you heard him. And he was starting on a project called the WOW signal. It all had to do with radio astronomy. So the more I started listening, the more I talked about it, I thought, you know, that sounds pretty interesting. So I started doing a little searching on cloudy nights, and I found some very interesting things. So I want to share with you tonight my interest in radio astronomy and what I'm doing, and hopefully pique your interest, and perhaps you'll want to get involved in it too. So let's take a look. All right, the electromagnetic spectrum. You've probably all seen this chart or one very similar to it many times in the past. The electromagnetic spectrum runs from extremely low frequency signals to really, really high frequency stuff, okay? So if we start out down at this pin over here, you see that we talk about wavelength in meters, that's 10 to the 3. So a wavelength would be about as big as a house at 10 to the 2, all right? Some of the things that happen around here are AM radio. You know, in the old days when we used to have AM radio, some of us still listen to that for baseball games, but regardless. So for instance, that stuff is down here in this area of frequencies. Now as we start going higher in frequencies, like for instance to FM radio, you get into 100 megahertz. These were down at 1 megahertz. These are up at about 100 megahertz. So the relationship is, in case you're not familiar with it, the frequency is in the number of the frequency is inverse to the number of the wavelength. So the shorter the wavelength, the higher the frequency. So as we're in this area here, again, we're around FM radio, and they talk about microwave ovens and radar and all that sort of thing. And as we go shorter and shorter in wavelength and higher in frequency, we see that eventually we get through radar and microwaves. And then once you pass there, you start getting into the light bands. Now, see that little place right there? That's all you get to see. Okay? Everything we do with visual astronomy is right there. Now that's pretty limited when you start looking at the overall scope of things. So, let's broaden our minds a little bit and see if we can figure out some other things to look at. Now, I don't really understand this chart, but I'll tell you what the book said about it. This is called the chart of black body radiation. Now, despite the sum, all mass generates energy, all right? And depending on the size of it and its chemical makeup, it gives off energy in different bands. Now, you can see that the wavelength down here changes, and as the wavelength gets longer and longer, no, shorter and shorter, excuse me, these must be, I've lost track.
Longer.
Yeah, it appears to be longer, but the intensity gets lower and lower. So the shorter the wavelength, in other words, the visible light area, the more energy that is given off in the visible spectrum. Now, we also have what we call absorption lines, and a lot of people work with that sort of thing in visual, because even though the band is very narrow, there's a lot that goes on inside there. And different elements absorb different wavelengths or react to different wavelengths when they are struck by those wavelengths, different elements. So spectroscopy is pretty common, and it's typically how they determine the chemical makeup of any light that's coming in from a star, from a planet. They can tell a lot about the chemical makeup based on the spectroscopy. However, there's other frequencies put out besides the ones in the visual spectrum. All of these elements that you see over here react to various frequencies. They all have specific frequencies that are associated with them. So it's like spectroscopy for radio waves. In other words, you can't see it, but if you can detect the frequency, then perhaps you can get some idea of the elements that are involved. Now, what I want you to do is to remember this one right here. That's my baby, 1420.406. We'll learn a lot more about that as we go on. Now, these frequencies are what's called protected. The international somebody, whoever's in charge of that sort of thing, has said, thou shalt not transmit on these frequencies because they're known to be useful in astronomical work. So it's unlikely that if you see a signal in these bands, that it's going to be man-made. So that's a good thing that helps out the kind of work that we're doing. Now, here's my little hydrogen friend. Now notice that the electron is spinning around, and every once in a while he has to change his position. And there he goes, spin in your own direction. And when he does, he changes state. And when that happens, he gives off a frequency of 21 centimeters, or 1420.406 megahertz. Now, another good thing is that our atmosphere blocks a lot of harmful radiation from reaching us. That's the only reason we exist on Earth. One of the reasons is because our atmosphere blocks a lot of this stuff in this area here. Okay? It just barely lets through the visible spectrum right here. As you can see, right here we have all of our visual telescopes, and the upper, the gamma rays, X-rays, and ultraviolet, the lower frequencies are pretty much blocked, or the higher ones I should say, are pretty much blocked, which is a very good thing for us. And then other gaps in it. But way over here, we have the radio spectrum, which goes down to about 10 meters, which is about 30 megahertz. So when we talk about, for instance, you may have heard CBers talk about skip, okay? What happens with skip is that the frequencies are lower than 30 megahertz, so they bounce off the ionosphere and come back to Earth. Higher frequencies pass through the ionosphere, plus it doesn't block. So here we have our area of interest here in the 21 centimeter band, right about here. So what does the radio sky look like? Can we actually figure out a way to visualize? Can we transfer RF energy to something that we can visualize? Well, yes, we can. It kind of looks like that. Now, this is a sidereal chart of the sky. So, as we look in this area, we can see that all the 24 hours going across and various degrees of, I believe this is as declination altitude. So in the radio in the sidereal sky, you're always looking in the same direction if you look at a set of sidereal coordinates. And sidereal time is always based on the first point over here, and then as we go across. So for instance, if you only looked at one spot and the Earth is spinning on its axis, it's really important to remember that the Earth spins on its axis. It's crucial to our work, plus our life. So as we look in this area, right over here, we can see that if we only stare here, this will eventually move across the sky. All right, now I'm going to show you a better example of that in just a moment. Now this was, let me go back. Oh, too far. Oops, wow. All right. Now, notice right up here, see that little spot? That is the strongest radio signal in the sky. Okay, this is essentially the center of our Milky Way. But this is brighter than that. And that is something that we call Cassiopeia A. It's basically a remnant of a supernova that's out there, and it's really hardly visible with telescope or visual equipment, as you can see here. But in the radio spectrum, when we convert strengths of radio energy into various colors, it looks like that. So that is the strongest thing. So whenever somebody comes to me and says, you know, I'm having trouble getting my scope to align. What do you recommend? I said, well, look at the brightest thing you can find. Find the moon. Focus on the moon. If you can focus on the moon, then you can start working toward less and less bright objects. Well, this is going to be the goal for a first-time radio telescope, is to find Cassiopeia A, because it's the brightest object and far and away the strongest signal in the sky. All you got to do is find it. So what does the rest of the radio sky look like? Well, it all depends what frequency you're looking at. And this is a very important concept in radio astronomy, is what frequency are you looking at? Now here, we see all different frequencies, okay? This is 408 megahertz. I'm not sure why some of these were selected, but regardless, these are various frequencies in what is seen. Now down here, we have our optical sky. That's what you see on a good, clear night in the dark sky. That's what the Milky Way would look like. But all of these other images are different other frequencies. Infrared, molecular hydrogen, and my own personal favorite, yeah, that would be, I think this is the atomic hydrogen here. That's the one, theoretically, that's what it would look like. So there's lots and lots of different ways to look at energy coming out of the sky. All right, so what do the professionals use when they do this? Well, they have more money than me. So they start out with perhaps something down in Arecibo. Now this is the largest, depending on if you accept the news articles about the Chinese, this is the largest radio telescope in the world. It's been around for about 40 years or more. And the biggest problem with it is, it's not steerable. It is slightly, because the part up here at the top can be beamed in different parts. So I believe it's got about a 10-degree, maybe a little more, I'm not sure. It can be steered slightly. But again, they base it essentially on whichever part of the Earth is where it's pointing. So then we start going in different direction, and we look at the VLA, a very large array out in Arizona, New Mexico, I'm not sure. But they have 27 different dishes like this, and they can all be moved. And the trick here is that they can combine the signal from all of them together through the magic of their computers and receivers. And so it's basically like having a dish that's 30 kilometers wide. Now that's a good size dish. Now I want you to remember how impressive all of these dishes are, because in a moment I'm going to tell you that that's only half the battle. The size of the dish matters, but not as much as what's behind it. So now we get into one of the largest single movable dishes in the world. This is at Green Bank, West Virginia, the National Radio Observatory. Now, Green Bank and the observatory is a very special place for anybody who does radio astronomy. First of all, they have special cars there. I understand they're still running like 1972 checker cabs with diesel engines. Anybody know why they use diesel engines? No ignition noise. There's only 2 microwaves in the whole city, and they are inside of screened-in rooms. Okay, no cell phones, no Wi-Fi, no nothing, no radio signals. Now, there have been a number of stories about people who go there because they claim that radio energy is affecting them. So they go there and they say, well, they immediately feel better. Well, that's a good thing. I hope that it works for them. But there is very, very little radio noise. And you notice that it's surrounded by mountains. So that blocks out a lot of energy coming from other areas as well. So, how does amateur radio astronomy work with professionals? Well, there's actually quite a bit. Just as much as visual amateur astronomers can contribute to things like finding supernova, or perhaps observing something that happened on Jupiter before anybody else. Because the pros are not out there looking all the time at general things. They're, dedicated to whatever it is they got their grant money for. So they're not always looking everywhere like the amateurs are. Now, I know that there have been a number of things, especially on Jupiter, right, Craig? Yep. That have been discovered by amateurs before they were seen by the professionals. There have been a number of supernova identified by amateurs before the professionals saw them. So just that same way, in radio astronomy, there are things that amateurs can do. For instance, in the various bands, depending, and again, it's all frequency dependent. If you're not familiar with the frequency bands, then that's a basic understanding that you kind of need to get up to speed on. But in the various frequency bands, there's all kinds of work going on. In different things occur in different parts of the band. So we have Earth-based phenomena, typically in the SLF range, which we call all the way from 30 hertz to 300 hertz, ULF, ultra-low frequencies, and these are all, they would be in the audio range, except they're electromagnetic. Remember, what we hear is vibration of the air. We don't hear electromagnetic vibration. These frequencies are around us all the time. Let me give you an example. Did you ever think about nuclear submarines that have missiles? How do they decide if they should fire a missile? Well, the problem is that you can't if you get knocked out, you might not be able to send them a signal to send their missile. So what happens is that there is a constant, very low frequency signal constantly going out that can be received by the submarines underwater. As long as they hear that signal, they know they should not fire their missile. But if that signal goes away or they hear something on it, then they start going into their books and finding out what it is they're supposed to do. So you're constantly being, the ultra low frequency is always around us. Just like the 60 hertz from lights and the super low frequency stuff is always around us. So depending again on what frequency we're looking at, there's different areas that you can study. And we'll see some more of these a little bit more. There's something called SIDS, Sudden Ionospheric Disturbance Radios. And that's actually another part that you can get into fairly inexpensively. In what we call the HF range, and if you're into amateur radio, you're very familiar with this, from 3 to 30 megahertz. This is where most of the stuff happens that goes worldwide. Now remember that drawing we showed about the ionosphere basically allows the ionosphere will bounce back those signals under the right conditions. So those signals can go all over the world. Whereas when you start getting into higher frequencies, you get into frequencies that penetrate the ionosphere and will continue to go straight on up. But some of those can be used, for instance, for meteor detection and signals bouncing off of ionized gas. Jupiter has storms due to charged particles, solar flares, etc. Now, as we go higher and higher in frequency, we get up to this area, which is my area of interest currently, 300 to 3,000 megahertz, or 3 gigahertz. So we have what's called continuum drift scan, and I'm going to show you what drift scan is. That's one of my favorite things about this. And then we get into the super high frequencies, 3 gigahertz to 30 gigahertz and above, and all these things. And we have SETI and lots of other things going on down in here. So, you want to get started? Build an itty-bitty telescope. The IBT. This can be built out of an old TV satellite receiver that people throw away. I often see them thrown away. They're easy to come by. It won't give you much because, again, size matters. But regardless, it will pick up some signals and because it's steerable and it's small and it does have a beam width, you can tell that a signal is coming from a certain direction. Now the other area that we have is, let's see if I can find my notes on that. A lot of times you can use receivers at various frequencies, and by measuring where the signal hits the ground, if you happen to be in a place, if you know where the antenna is, the AM antenna, and if you're picking up a signal here from, say, Chicago, then you know that the ionosphere has to be pretty much at a certain height. It gives you some idea of measuring the various layers and how they're affecting what's going on. Now, this was the SID that I was talking about. Super SID, which is a program from Stanford University that gathers information about sudden ionospheric disturbances. The system works by monitoring VLF radio stations, only 15 to 30 kilohertz, barely above normal hearing range if it were sound, and watches their signal strength change. Whenever the Earth's ionosphere is disrupted, by either solar wind or possibly a gamma ray burst, the signal strength changes. The system is easy to build and bring online for automatic data collection, and you can upload the data to a Stanford and a NASA facility. They collect all this data, kind of like what they do with the SETI program. The receiver is pre-assembled. You can buy it. You can buy it for like $200 or less. Build a small antenna array, and you can begin to start collecting data to feed into the database for measuring ionospheric disturbances. Now, some of the equipment that you get will put out charts such as this. These are kind of inverted because if you turn them around, these are actually peaks and not valleys. So these are the kinds of things that you get for information coming off the sun. So again, as you gather this data, you feed it into various databases, and they take all of the data that people submit and get an idea of what's going on with the atmosphere and can gather information that way. Now Jupiter, Radio Jove, as it is sometimes referred to, puts out a lot of information. That's another whole area of study, just studying information or electromagnetic energy coming out of Jupiter. And unfortunately, I don't have that. Okay. But there is a whole series of radios that you can buy. Radio Jove, this is a website you can go to. You buy this little receiver. It takes a little bit more of an antenna, a little bit larger, so you have to have a little room to space it out. But this is a basic radio, and it feeds into a PC, into the audio input, and based on that, it gives you information about electromagnetic energy coming off of Jupiter. And again, people collect this data and compare it worldwide. Now, Brian, are you going to talk about Astro League, these awards?
Not to the extent, I mean, you can go ahead.
Well, I mean, all I was going to say is that you'll learn later, if you have not learned already, our club promotes the Astronomical League in what they call these observing clubs. They have created two different levels of radio astronomy. Basically, one, the blue one, is just for doing one. There's 4 different activities, and they're all in different frequencies. Pretty much what we talked about. There's one for the SIDS, there's one for Radio Jove, and there's one for basically what I'm doing in the hydrogen area. So when you get one of these, you get the blue badge. I think if you get 3, you get the gold badge. So there's a lot of information on the Astronomical League, astroleague.org, and look up radio astronomy and to find out more about what they offer and the steps to go through to get it. So, what does my cheap little setup look like? Well, what I discovered is that a radio telescope in my frequency range of 21 centimeters basically consists of 3 parts. First of all, you've got the dish, or some way to collect the signal up in here. I hope my guys working. So you've got your dish, and then this is very important. Think of this as the mirror in a standard Dove type telescope, or more correctly, perhaps a Cassiopeia. So think of this as the mirror. Now here is something we call the LNA. The LNA stands for Low Noise Amplifier. And this is critical because the signal obviously coming in is very, very weak. Now you can't have your PC at the front of the antenna. That would not be realistic. So what you do is you have to have a cable that comes down. The cable that I use here from my LNA into my next block is about 25 feet long. Well, even a minuscule amount of loss in that cable may just wipe out whatever signal you're receiving. So we start out by at the antenna we have what's called a feed horn. I'll show you more about that in a minute. And on the feed horn, you mount an amplifier at the frequency range that you're interested in. So we have the LNA, the low noise amplifier. And then we come down here to basically what is the receiver. Now receivers can take many shapes and sizes. But what really got me started in going in this direction was this little box right here, the RTL SDR. And again, I'll show you more about that in a minute. And that feeds into a PC and you've got software. So think of this as being the main mirror on a telescope, this as perhaps being an eyepiece, and this being a camera that's, if you're into imaging, and then feeding that into a PC for processing your signal. So the analogy is similar, except that the LNA acts as both eyepiece and a camera up here. So, the RTLSDR.com, the RTLSDR. This is it. That costs $29 on Amazon. And the SDR stands for Software Defined Radio. This is capable of receiving signals from, I think, like 3 megahertz up to over 3 gigahertz. You can receive FM radio. It was originally designed to hack into television stations. Okay? I think that was all on analog though, so now that you go on to digital, it really doesn't work that way. But it works really nice at 1.4 to 0.4 gigahertz, which is where I want to listen. So this is my radio. It costs $29. I was willing to splurge $29 to get into this to see if it worked. So let's keep going. Now this is my LNA, okay? I had to go a little higher on this. I had to spend a little bit more money. This has 3 amplifiers in it. There's 1, 2, and 3. This part right here is a frequency filter that only allows a band pass of about 1.3 to 1.5 gigahertz to pass through it, because I don't want to amplify everything. So the input coming from my feed horn is over here, and I've got the feed horn here. I'm going to show that to you. And that feeds into an amplifier, which basically each amplifier is about 20 dB. So we've got somewhere, I've actually had it measured by a commercial lab, and I'm getting a total of 56 dB of gain through here. We'll talk about that some more in a minute. So this is the whole setup. This is my feed horn. Notice how elegant, made out of an old turpentine can. The LNA is mounted on top of it, and it's fed, it's powered by this power supply, and the whole thing then comes out of this cable, which feeds into the RTL SDR and into the side of my PC. Okay, so this is the feed horn, and the power cable that goes with it. Notice the amplifier chain here, just like in the picture. The amplifier chain, all the pieces in it cost about $140, something like that. And I made up the brackets and mounted it all on there. When you get a chance, look down inside here, there's a little tiny piece of wire. That's the actual antenna, okay? And it feeds up through the can right here and then into the first amplifier. So the little tiny piece of wire essentially is a quarter wavelength at 21 centimeters, and it detects the signal and has some bandwidth just because of its size. And then of course the filter also filters out everything outside of the area of interest that I'm looking at.
Question.
Yeah.
When you say the filter removes
electronic in nature, and it has components inside that only allow frequencies that I'm interested to pass. The other ones they block out. So yeah, I'm only interested in that one frequency for the time being. That's all I want to look at is the hydrogen line or 1.4 gig. Okay? So the first thing you got to do is get a dish. This is my dish. It's a 10-foot dish, 3.3 meters. I found it, I put an ad on Craigslist and said, I'm looking for a dish. So this guy comes back and says, well, I got a dish. He says, I said, well, how much you want for it? He said, oh, I don't know, how about $50? I said, yeah, I'll give you $50. Does it have a mounting bracket? He said, yeah. So I went over and looked at it. He was in Hudson. So I went over and looked at it, and it's 10 feet wide. I don't have anything I could haul a 10-foot wide dish with. So I said, well, it was at a tree trimming company. They had all kinds of equipment. I said, well, maybe you could put it on one of your trucks and take it over to Dade City for me. That's where I have it set up. Oh, yeah, I can do that. I said, I'll tell you what, I'll give you $125 if you bring the whole thing over to Dade City. Yeah, no problem. So we set up a time, and the guy rolls up and has it, no problem, unloads it. He says, yeah, I had an escort coming over here. I said, what do you mean an escort? He says, well, I came over on, 52? I guess 52, yeah, into Dade City from Hudson. He said, as soon as I got on 52, a sheriff's deputy came up behind me. This thing is sticking out 10 feet wide. He got it on the back of his pickup truck. I said, well, did he stop? No, he said, he got in front of me and escorted me all the way into Dade City. Super job. So there's the dish. That guy on the right there is my friend Butch. He's the one that owns the property up in Dade City. So, if you get a dish like that, it's dirty. Well, you got to wash the dishes. So I washed the dish, and we got it all cleaned up. And then we had to figure out whoever took this thing down never thought about reusing it. So they cut it off at the ground with a torch. Okay, fine, Well, obviously, something has to go in the ground to hold it up. Well, I called around to different welding companies, and it would have been like $200 to have somebody come out and weld a piece of pipe on the bottom of that. So I said, well, I haven't spent that much on anything yet. So we started thinking, we said, well, we'll take a couple of pressure-treated 4x4s and bolt it to it. So we drilled some half-inch holes through the pipe and put a couple of 4x4s on there to go in the ground. All right, so that took care of that part, and then we dug a hole and we put it in the ground. So that's all there was to it. Piece of cake, nothing to it. Now this is the feed horn bracket assembly, okay? This box fits very nicely right inside this area here, okay? And then the wires feed down these poles. The supports are made of PVC, and this is half-inch EMT electrical pipe that's nice and galvanized. I flattened one end, bent it over, and there's a screw holding it into the wood. So that's all there is to holding this in place. The measurements supposedly are critical. I'm sure it's like collimating any other telescope. The closer it is, the better it is. But there's a lot of experimentation and playing around that has to be done. All right, technical stuff. Theoretically, the gain from a dish is about 31 dB. So for those of you who understand gain and radio and stuff like that, 31 dB for the dish. The gain from the LNA, my noise amplifier, low noise amplifier, is 56 dB. That's been measured. I know that exactly. And the gain from the receiver, as near as I can tell, is about 40 dB. So I basically have 127 dB of gain from the antenna feeding into the software. Now, again, if you're familiar with those numbers, that's a lot of gain, all right? So you have to be careful of what you point it at. You don't want to probably point it at the sun because it would, not the light that's going to hurt you, but just the energy coming off the sun could possibly cause some damage. So 127, theoretical, my guess is probably closer to 100 dB because I don't know how good my dish is. I don't really know what the gain of the radio is. And of course, there's some other areas that could have some loss. Now the beam width is about 4 degrees. Now these numbers all come from a paper that I got that was written by a guy called Taming the 10-Foot Dish. And he basically wrote out all the specifics on how to repurpose a 10-foot satellite dish to do this kind of work. He lives up in Chiefland, and he's a great guy. I went up to visit him, and he gave me his paper. I saw his setup, and his name is Tom Crowley. Maybe some of you have heard of him. He's a brilliant guy, and basically one of the gurus of the amateur radio astronomy community. So there's my whole setup, set up at Dade City. I have had it set up and run. I haven't done anything conclusive with it yet. It's just too darn hot. I hope to be, I may go tomorrow. I'm hoping my wife will talk me out of it. I may go up there tomorrow. We'll see. So, now, if you want to know how high the antenna is pointing, which is very critical, I thought I had moved this slide, but that's okay. I may have put it in another place too. This is a little magnetic, basically it's a level that you put on any surface, and as the antenna goes up and down, this part right here is actually like a worm drive motor, and I can hook a battery on there, and by this going up and down, it tilts the antenna either higher or lower. And then I can measure what angle it is using the magnetic level tied here to the frame. Now this is all presuming that the thing was put together right, that it's square, a lot of variables that I have no idea. So eventually, hopefully I'll find a signal that I can beam on, and we'll be able to get some idea of whether or not how close it is by going up and down. Left and right is just controlled by Armstrong power. So, and there's a feature for that that's actually not too bad. We'll see about that in just a minute. So, software, you have to have some software. SDR stands for Software Defined Radio. Well, it turns out the software is free. So that worked out nicely. I like that. So there's 2 different kinds of software that I'm playing with. The first is called SDR Star. They call it SDR Star, SDR Sharp, whatever. And it's really nice, and it gives a good example of various signals. For instance, this might be, as you can see right here, this is 1.419. Now, it's very possible that the hydrogen line signal won't be at exactly 14.02, or whatever I said, 14.20, because of Doppler shift, okay? It's just as subject to Doppler shift as anything in the light band. So, if you happen to be receiving a signal from some hydrogen that's moving away from you, it's going to be Doppler shifted. And just the reverse, if it's coming towards you, it may be Doppler shifted. And in fact, this is one of the things that people do with this frequency. If you point it toward the Milky Way in a direction that is coming toward you, you'll see it Doppler shifted in one direction. If you turn your antenna around to look at the other side of the Milky Way, you're going to see that the Doppler shift is longer wavelengths, which means, of course, it's moving away from you. Now, this is really good software. It gives a lot of information, but there's one thing it didn't do that that I found critical, it doesn't record. You can't record this data anywhere. I mean, it's like looking through an eyepiece. You get to see a lot of nice stuff, but it's only what you remember. Now, I took a video with my cell phone and watched as the signal went through, but, that's relatively limited. So I started looking around for some other software, and I found this stuff called Radio Sky. It was pretty much developed just to do the kind of work I'm doing. And it gives a chart recorder, and I've got a few examples I think I can show you. Let me see. I want to go through this more, and then we'll go back and see some other stuff. All right, drift scanning. This is one of my favorite topics. As I said, the antenna can go up and down, but, only with like a motor. I can, tell it I want to be at 40 degrees, 45, whatever. But, left and right is strictly based on me moving it by hand, and I don't have a real good way yet of determining what direction it's pointing. Well, remember Arecibo? They can't move that, okay? But the Earth is spinning, people. So if it's out here, as the Earth spins, it's drift scanning, okay? That's the meaning of the term. So, let me show you this example. I'm going to bring up another program. Good old stellarium. So we'll make it be nighttime, and we'll come down here a little bit, and we will turn on the meridian. There it is. Okay. So let's say that somehow I can figure out how to point my antenna due south. Okay, no problem. That's really not that big a deal. I can sort of figure out south within a couple of degrees. So now let's say that I want to look at this area. Guess what? That's the center of the Milky Way. How do I know that? Because, well, if I turn on my constellations, there's Sagittarius, and his arrow points toward the middle of the Milky Way. More or less. Pretty close. Okay? So, now, if I point south, so now all I've got to do is find a star somewhere in this vicinity. And look at there. Stellarium shows me everything I could possibly want to know about where that star is. It gives me its right ascension and declination. But what it really gives me that I'm interested in is its altitude and azimuth. Okay? So right here it's telling me that its altitude is 29.57. So I can now take that little magnetic level on the back of my scope and set it so that my dish is tilted 29.57 degrees above the horizon. Now, if I am watching at this time of day, I can watch, and I'm going to speed up the clock just a little bit here, but watch what happens to that star. I don't have to move anything. As the clock moves, obviously, that star moves across the meridian, and theoretically, through the beam of my dish. Okay? Now, if I see an increase in signal at that point, I know I'm pointed in the right direction. So I can just let it run, record all that, go back later because my software records. The biggest thing here is keeping accurate notes like anything else because you got to know how high your antenna was pointed, what time it was exactly, and when the signal went through. So all these various points